Welcome to this series on neural network programming. We're ready now to begin building our first convolutional neural network using PyTorch. Without further ado, let's get started. From a high-level perspective or a bird's-eye view of our deep learning project, we have prepared our data and now we are ready to build our model. When we say model, we mean our network. The words model and network refer to the same thing. What we want our network to ultimately do is model or approximate a function that maps an image input to the correct output class. When we first started this series, we said that the Deep Learning Fundamentals series was a good prerequisite, and now is the time that those details will come in handy most. So if you find yourself struggling, or if you just want a crash course on CNNs, these are the specific posts to see. For now, let's jump in with a quick object-oriented programming review. To build neural networks in PyTorch, we extend the torch.nn.module PyTorch class. This means we need to utilize a little bit of object-oriented programming in Python.
Why, as data scientists, do we care about object-oriented programming? Because a lot of the stuff you use is going to require you to implement stuff with OOP. For example, every single PyTorch model of any kind is created with OOP. It's the only way to create PyTorch models.
When we're writing programs or building software, there are two key components, and those components are code and data. And with object-oriented programming, we orient our program design and structure around objects. Objects are defined in code using classes. A class defines the object's specification or spec, which specifies what data and code each object of the class should have.
The words object and class are at the top of the list of object-oriented concepts. It's important to make the distinction between the two. A class is like a blueprint or a description of an actual object, while the object is the thing itself. It's what the class describes.
When we create an object of a class, we call the object an instance of the class. And all instances of a given class have two core components. Number one, methods, and number two, attributes. The methods represent the code while the attributes represent the data. And these methods and attributes are defined by the class.
We can think about attributes as describing the characteristics of an object, and methods as the behaviors of the object. For example, if we had a lizard object, some attributes it may have are color and length. Some methods it may have are run, jump, and catch a bug. So in other words, the attributes are properties of the object that let us know the object's characteristics, and methods let us know what the object can do.
In a given program, many objects, aka instances of a given class, can exist simultaneously. All of the instances of a particular class will have the same available attributes and the same available methods. They are uniform from this perspective.
So think about it this way. The lizard class lets us know that a lizard object has a color and has a length, but it doesn't tell us what the color or what the length is because the class only describes the object. Remember, a class is like a blueprint of an object, and actually, we can make as many different objects as we'd like from the same class. For example, one lizard object made from the lizard class may be green with a length of 20 centimeters, and another lizard object made from the same class might be brown with a length of 10 centimeters.
The difference between objects of the same class is in the values contained within the object for each attribute. Each object has its own attribute values. These values determine what is called the internal state of the object, and the code and data of each object is said to be encapsulated within the object.
Classes are said to be self-contained units that represent both the code and the data. So you can think of this as kind of packaging up the attributes and the methods together and encapsulating them inside of the class.
Once we have our classes designed, we create instances of our classes to perform tasks inside our programs. So let's build a simple lizard class to demonstrate how classes encapsulate code and data. The first line declares the class and specifies the class name, which in this case is lizard. The second line defines a special method called the class constructor.
Underscore underscore init underscore underscore is a special magic method that's called when you try to construct a class. So when I call tree ensemble parenthesis, it actually calls tree ensemble dot. People say dunder init. I kind of hate it, but anyway, dunder init, double underscore init, double underscore dunder init. So that's why we've got this method called dunder init. Okay, so when I call tree ensemble, it's going to call this method.
Class constructors are called when a new instance of the class is created. As parameters to this particular constructor, we have a parameter called self and a parameter called name. The self parameter is a special parameter that gives us the ability to create attribute values that are stored or encapsulated within objects of the class. When we call this constructor or any of the other methods, we don't pass an argument for the self parameter. Python does this for us automatically behind the scenes.
The older languages like Python often did this because they kind of needed to, they started out not being OO, and then they kind of added OO in a way that was hideously ugly. So Perl, which predates Python by a little bit, kind of, I think, really came up with this approach, and unfortunately other languages of that era stuck with it. So you have to add in this magic self.
Argument values for any of the other parameters are arbitrarily passed by the caller. And these passed values that come into the method can be used in a calculation or saved and accessed at a later time.
So the magic self now, when you're inside this class, you can now pretend as if any property name you like exists. So I can now pretend there's something called self.x. I can read from it, I can write to it, right? But if I read from it and I haven't yet written to it, I'll get an error. So the stuff that's passed to the constructor gets thrown away by default. Like there's nothing that like says you need to, this class needs to remember what these things are. But anything that we stick inside self is remembered for all time. You know, as long as this object exists, you can access it, it's remembered.
After we're done with the constructor, we can create any number of custom methods like this one here that allows a caller to change the name value that is stored inside self. All we have to do here is call the method and pass a new value for the name. Let's see this in action. We create an object instance of the class by specifying the name of the class and passing the constructor arguments. The constructor will receive these arguments and the constructor code will run, saving the pass value for name. We can then access the name and print it, as well as call the setName method to change the value of name by passing in a new one.
So inside an object, there are kind of two kinds of things. There are the functions that you can call. So you have object dot function parenthesis arguments, or there are the properties or attributes you can grab, which is object dot and then just the attribute name with no parentheses.
Multiple of these lizard instances can exist inside any single program, and each one will contain a copy of its own data. From an object-oriented standpoint, the important part about this setup is that the attributes and the methods are organized and contained within an object. Let's switch gears now and look at how object-oriented programming fits in with PyTorch. To build neural networks in PyTorch, we use the torch.nn package, which is PyTorch's neural network library. Hence the name NN for neural network. We typically import the package and alias it as NN. For our code, this means that from now on, if we say NN, we mean torch.nn. PyTorch's neural network library contains all the typical components needed to build neural networks. the primary component we need to build a neural network is a layer. And so PyTorch's neural network library contains classes that aid us in constructing layers. Each layer in a neural network has two primary components. Number one, a transformation, and number two, a collection of weights. Now, if we think back to object-oriented programming, we might be able to see that a transformation is probably represented using code, and a collection of weights is probably represented using data. So keep that in the back of your mind as we go forward. This fact makes layers great candidates to be represented as classes using OOP. OOP is short jargon for object-oriented programming. PyTorch layers are defined by classes, so in code, our layers will be objects. Within the neural network package, there is a special class called module, and it's the base class for all neural network modules. This means that all the layers in PyTorch extend the nn.module class and inherit all of PyTorch's built-in functionality that comes with the nn.module class. In OOP, this concept is known as inheritance. If you extend a class, then you get all of its functionality. This includes layers, and this includes neural networks. If you think it's a little strange that neural networks and layers should inherit the same functionality, just consider that a neural network can be thought of sort of as one large layer. Layers are functions, and neural networks are composed of layers. And a composition of functions is itself a function. So in general, layers and networks are sort of the same type of object. And in PyTorch, these similarities are captured inside the neural network module base class. This means that we should extend the module base class anytime we are creating a custom layer or a PyTorch neural network. That's the first step. Let me tell you about the next key piece, which is the forward method. When we pass a tensor to our network as input, the tensor flows forward through each layer transformation until the tensor reaches the output layer. This process of a tensor flowing forward through the network is known as a forward pass. Each layer has its own transformation, and the tensor passes forward through each layer's transformation. The composition of all of the individual layer forward passes defines the overall forward pass transformation for the network itself. What this all means for PyTorch is that every PyTorch nn.module has a forward method to represent the forward pass. And so when we're building layers and neural networks, we must provide an implementation of the forward method. The forward method is the actual transformation, whether it's for a layer or for a neural network. This brings us to the last piece. When we implement the forward method of our nn.module subclass, we typically use functions from the nn.functional package. This package provides us with many neural network operations that we use when we're implementing our forward functions. So this gives us the three key pieces of information we need to create a neural network class in PyTorch. Let's summarize this and then we'll build an example. Number one, create a neural network class that extends the neural network module base class. Number two, in the class constructor, define the network's layers as class attributes. And number three, use the network's layer attributes as well as operations from the nn.functional API to define the network's forward pass. Let's create a simple class to represent a neural network. This gives us a simple network class that has a single dummy layer inside the constructor and a dummy implementation for the forward function. The implementation for the forward function takes in a tensor t and transforms it using the dummy layer. After the tensor is transformed, the new tensor is returned. So this is a good start, but the class hasn't yet extended the nn.module class. To make our network do this, we must do two additional things. Number one, we need to specify the nn.module class in parentheses on line 1. And number two, we need to insert a call to the superclass constructor on line 3 inside the constructor. So let's do that now. These changes transform our simple network into a PyTorch neural network because we are now successfully extending the PyTorch nn.module base class. With this, we now have a network class that has all of the functionality of the PyTorch nn.module class. The benefit of this is that underneath the hood, the module base class is keeping track of the network's weights, which are contained within each layer. And what we'll find is that this feature is going to be super handy during the training process when the weights need to be updated. At the moment though, our network class only has a single dummy layer as an attribute. So let's replace this now with some real layers that come pre-built for us from PyTorch's neural network library. We're building a CNN here, so the two types of layers we'll use are linear layers and convolutional layers. Alright, at this point we have a Python class called network that extends PyTorch's nn.module class. Sadly, there's actually a bug in this code. If we try to create an instance of this class, we'll see an error. It was already there before we added these layers. As a challenge, see if you can identify the bug. Leave your answer in the comments.
Interestingly, I was able to instantiate tree ensemble even though predict refers to a method of decision tree that doesn't exist. And this is actually something very nice about the dynamic nature of Python, is that because it's not like compiling it, it's not checking anything unless you're using it, right? So we can go ahead and create decision_d.predict later, and then our instantiated object will magically start working, right? It doesn't actually look up that method's details until you use it.
So let's look at these layers now. Inside of our network, we have 5 layers that are defined as attributes. Each of these layers has 2 components, a set of weights and a transformation that is defined inside the forward method. We have 2 convolutional layers, conv1 and conv2, and 3 linear layers, fc1, fc2, and out. We use the abbreviations FC in FC1 and FC2 because linear layers are also called fully connected layers. So that's where we get that FC. Linear layers also have a third name that we may hear sometimes, which is dense. So linear, dense, and fully connected are all ways to refer to the same type of layer. PyTorch uses the word linear, hence the name nn.linear as the class name. We use the name out for the last linear layer because the last layer in the network is the output layer. We can get an instance of our network by calling the constructor. With this, we should now have a good idea about how to get started building neural networks in PyTorch using the torch.nn neural network library. In the next post, we'll investigate each of these layer parameters very closely, which will give us a better understanding of each of the individual layers and the overall network as a whole. Check out DEEPLIZARD.com for additional resources and have a look at the HIVEMIND, where you can get DeepLizard perks and rewards. Hit the like button to support collective intelligence, and I'll see you in the next one.
It all started 6 years ago with the AlexNet. Alex Krzyzewski, as I mentioned before. It was only 8 layers deep, and about 1 million parameters, 1 million numbers. This body of computational graph was 8 layers deep, about 1 million parameters. In just that short time, and this one network ignited the revolution of modern AI. It was able to solve a problem that is essential for artificial intelligence, for software to interact with the real world, by discovering the important features of a large amount of unstructured data automatically. The front layers, the convolutional neural network layers, was able to discover the essential patterns that would classify an object, and it did it automatically. You don't have to write any software. You just have to give it a lot of data, and it needs a lot of supercomputer, to be able to discover the interesting patterns out of information by itself. It's like you and I being able to discover patterns out of experience. We live in experience, we do something, and over time we say, hey, this pattern exists, and it keeps emerging. And then we generalize that pattern into knowledge, otherwise known as intelligence. The ability to recognize features, recognize important patterns, create the structure of the data, of the patterns, and generalize it hierarchically into knowledge, revolutionized modern AI. From there, it just took off. Look at that. People thought that CNN was the beginning and the end. It was just barely the beginning. Since then, Cambrian explosion, just literally every single type of neural network has happened. CNNs, not only has it gotten more complex, different layers are all created. RNNs to recognize sequential patterns. CNNs recognize spatial patterns. RNNs recognize sequential patterns. The combination of the two does amazing things as well. You also have generative adversarial networks. A neural network, that's essentially two networks. One network trying to generate an image. Let's use image as an example. One of them generate an image, generate a sound, or generate a story. Okay? One of them is generating. The other one is testing the output of the generation to see, is it good? Is it real? Is it good enough? And the two of them are competing with each other. That's why they call it adversarial. It's generating, it's a generation network, but it's adversarial. And as a result, when both of the networks become super good at generating new ideas, the other one testing to see if it's good or real, the GAN generates outputs that are basically superhuman. And so generative adversarial networks, reinforcement learning is like the way we learn. Trial and error, try this, try that. When we're learning how to walk, we use reinforcement learning. We try it, and if we do a good job, we get a reward. If we do a bad job, you get a disincentive. And so you try it over and over and over again. This is how we're going to teach robots how to be good robots. And then there's all kinds of new species that are still coming out. In just 6 years' time, thousands of neural networks have been invented, and the complexity of it is incredible.